Hello, I am Onok Mundol, lecturer of Mechanical Engineering Department, Camellia Institute of Technology and Management. So let's start to today's session of PCME 502, that is the solid mechanics. So in our previous class, we saw that if the plane is if we take another frame, that is x dash y dash z dash instead of x y z, and if the shear stress if the rectangular stress components are sigma x, sigma y, sigma z, tau x y, sigma x dash, sigma y z, sigma z dash, tau x dash y dash, tau y dash z dash, tau z dash x dash. So we can see that sigma x plus sigma y plus sigma z is equal to sigma x dash plus sigma y dash plus sigma z dash, and the coefficients of the previous determinant we take that L1, L2, L3. So the coefficients are equal to that L1 is equal to L1 dash, L2 is equal to L2 dash, and L3 is equals to L3 dash. So if we take another frame x dash, y dash, z dash, another reference frame, we better to write another reference frame x instead of x, y, z, and if rectangular stress components are sigma x dash, sigma y dash, sigma z dash, tau x dash y dash, tau y dash z dash, tau z dash x dash, we can write that sigma x plus sigma y plus sigma z, that is equals to sigma x dash plus sigma y dash plus sigma z dash, and the coefficients of previous determinant equation we take as L1, L2, L3. So here if we take that L1 dash, L2 dash, and L3 dash instead of L1, L2, L3, so we take as L1, L2, L3, and then L1 is equal L is equal to L1 is equal to L1 dash, L2 is equal to L2 dash, L3 is equal to L3 dash. Okay, now the principal stresses at a point depends only on the state of stress at that point and not on the frame of reference describing the rectangular stress components. So here so hence if x y z and x dash y dash z dash are two orthogonal frames of reference at the point, then the following cubic equation is something new, that is sigma cube. At first we have to write that the principal stresses, we know the principal stresses at a point, depends only on the state of stress, depends only on the state of stress at that point and not on the frame of reference describing the rectangular. So describing the rectangular stress components. Hence, if x, y, z and x dash, y dash, z dash are two orthogonal frame of reference at a point, then we have cubic equation. We have following cubic equation, and that is sigma cube minus L1 sigma square. This is the coefficients of previous determinant equation, that L2 sigma minus L3 is equal to 0, and in other way we write L1, and here this is the determinant equation if we take the plane xyz, and this is I'm writing that L1 dash sigma square sigma L1 dash sigma square plus L2 dash sigma minus L3 dash. This is the determinant equation if we take the x dash y dash z dash plane instead of xyz plane. Okay, so then this this second equation must give what to write must give the same solution as previous we get. Okay, since so why we get same solution as previous, because we see that the principal stress at a point, this all the principal stresses at a point, this is the sigma, the value of uh, sigma if we evaluate in sigma 1, sigma 2, sigma 3. So the principal stresses at a point depend only on the stress of state of stress at the point, and not on the frame of reference. So we have the same solution as previous. So this is the explanation. I mean, this is the reason of this line. Okay, so now since the two system of axis were arbitrary, the coefficient of sigma square, sigma, and the last constant term in the two equation must be equal. So so we can write as a L1 I further write that L1 dash L2 is equal to L2 dash and L3 is equal to L3 dash. Okay. So now if we take only the value of principal stresses, we get the invariants are L1 that is equal to sigma 1 plus sigma 2 plus sigma 3, L2 that is sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1, and L3 that is sigma 1 sigma 2 sigma 3. Okay, sorry, if we take only the value of principal stresses, we get the invariants are L1 that is sigma 1 sigma 2 sigma 3, L2 sigma 1 sigma 2 sigma 2 sigma 3 sigma 3 sigma 1, and L3 that is sigma 1 sigma 2 sigma 3. So now we'll move the next another important topic, that is the next another important topic, that is principal plane in okay. So principal plane in principal plane are orthogonal. Okay, principal planes are orthogonal. So the principal planes corresponding to a given state of stress at a point can be shown to be mutually orthogonal. To prove this, we have to use the general theorem as I explained before, and I uh, again explain. Sorry, I'm explaining it again. That's only the statement of the general theorem, that a sorry the principal sorry the principal planes corresponding to a given state of stress at a point can be shown to be mutually orthogonal. To prove this, we make use we have to use the general theorem as I explained before, and I'm explaining it again. Only the statement, let let n dash n and n dash let n and n dash be the two principal planes. Okay, and sigma 1 sigma 2 are the corresponding principal stresses. Then the projection of sigma 1 in the direction n dash is equal to projection of sigma 2 equal to the projection of sigma 2 in the direction of n. So Tn n dash is equal to Tn dash n. Okay, so we can write that sigma 1 or Tn dash n dot n is equal to Tn dot n dash, or we can write that sigma 1 n dash into n, that is sigma 2 n into n dash. Okay, if nx, ny and nz are the directions cosine of n, and nx dash plus ny dash and nz dash are the direction cosines of n dash, then by expanding we get that uh, I write if nx, ny, nz and are the direction cosines of n and nx dash, ny dash, nz dash are the direction cosines of n dash, then we can expand it and write that sigma 1 and n dash 1 what? Nx, sorry, so we can write that sigma 1, this is the direction vector. Let this, we have to expand nx I cap n dash plus n y dash j cap plus n z k cap, and this is equal to, sorry, this is sigma n dash. So this dot, this is a dot product of nx cap plus n y j cap plus n z k cap. So is equal to sigma 2 into nx I cap plus ny j cap plus nz k cap dot product into, that is dot product with nx I dash I cap plus ny j cap dash plus nz k cap. So sorry, ny dash j cap and n dash nz dash k cap. Okay, so if we evaluate this dot product, we see that what is the dot product of this, that is nx nx dash I cap into nx I cap. This dot product of this, we get value, we get the value of nx dash plus similarly ny dash plus nz dash sigma 2, that is equal to sigma 2 n x nx dash plus ny ny dash plus nz dash. As wait as you know that dot product if I write a I cap plus b j cap plus c k cap dot product with a small I write x I cap plus y j cap plus z k cap, so we get the value that ax plus by plus cz. This is the solution process of the scalar dot product. So we can write that n x nx dash plus ny dash plus nz dash into sigma 1 minus sigma 2 that is equal to 0 because we okay, I have to explain that if we put this term to the left of this equation means okay, I simplify this for easily understanding. I'll simplify this PC 502. So I simplify this, that is sigma 1 nx dash plus ny dash plus nz dash minus sigma 2 nx dash plus ny dash plus nz dash that is equal to 0. So sigma 1 minus sigma 2, we take common nx dash plus ny dash plus nz dash is equal to 0. So as sigma 1 and sigma 2 are not equal, as sigma 1 and sigma 2 are not equal, then the only way to hold the above equation is, means if sigma 1 is not equal to sigma 2, so we definitely get that nx dash plus ny dash plus nz dash that is equal to 0. Okay, so as this is so we get that, we see that in this vector dot product we see that if nx I cap nx I cap dot nx j cap that is equal to 0, then definitely nx and ny placed in perpendicular to each other. Okay, so here if we see that if ai cap dot product bi cap that is equal to ab cos 90 degree that is equal to 0, if this if this value is equal to 0, so definitely the angle is 90 degree. Okay, so if this equation is 0, so nx and nx dash is perpendicular to each other, ny dash is perpendicular to each other, and nz and nz dash is perpendicular to each other. So if the total equation, so total solution of this previous dot product is the total solution of this previous dot product is 0, so we definitely say that n and n and n dashed are perpendicular to each other. Okay. Similarly, considering two other planes, n dash and n double dash, on which the principal stresses sigma 2 and sigma 3 are acting, and the following are the same argument as above. So we can say that n dash and n double dash are also perpendicular to each other. Okay. So similarly, if we consider two other planes n dashed and n double dashed, on which principal stresses sigma 2 and sigma 3 are acting. So by proceeding as same way as above, we can say that n dash and n double dash are also perpendicular to each other. Okay. Similarly, if we consider n and n double dash as two plane on which princip sorry principal stress sigma 1 and sigma 3 are acting, so we can say sigma n and n double dash are also perpendicular to each other. Okay. So we see that n and n dash are perpendicular to each other, n dash and n double dash are perpendicular to each other, and n and n double dash are perpendicular to each other. Means means the planes where sigma 1 and sigma 2 are acting, that is perpendicular to each other, and that belongs to n and n dash. The principal stresses sigma 2 sigma 3 are belong to n dash and n double dash respectively, and the planes are perpendicular to each other also, and the principal stresses sigma 1 and sigma 3 belongs to the planes that sigma 1 belongs to n sigma 1 belongs to n and sigma 3 belongs to n double dash. So the plane n and n dash are also perpendicular to each other. So hence we prove that the principal planes are mutually perpendicular, means n perpendicular to n dash n dash perpendicular to n double dash and n perpendicular to n double dash also. So see what I have learned, what we have learned in this lecture. Okay, so this class ends here. Thank you.